In 3.4, we'll use our implicit differentiation rules to solve word problems known as related rates problems. And we have a series of steps for a strategy. Not all of these steps will be used, but it's a good idea to follow these in order to take the proper derivative and then evaluate. So here in step 1, what you want to do is assign letters to all quantities that will vary with respect to time, and any others that seem relevant to the problem, and you would give a definition to each letter. So you would need to state that A is for area, V is for volume, and so on. In step 2, you would then identify the rates of change that are known and the rate of change that is to be found, and you would interpret each rate as a derivative. Derivative. Okay, in step number 3, what we want to do is make sure that we can find an equation or a formula that relates the variables and whose rates of change were identified in the previous step. And to do this, sometimes you're going to need to draw an appropriately labeled figure that would illustrate the relationship. Meaning if we're talking about a circle or a cone, or a cylinder, you want to draw all of those figures depending on the problem. So then in the next step, we would differentiate both sides. Okay, for the equation that we find will be appropriate in step number 3, and we're going to differentiate with respect to time and make sure that we produce a relationship between the known rates of change and the unknown rate of change. So for example, if you're trying to differentiate x with respect to time, if we had something like this, this would just be dx dt. Or if this was x squared, it would be 2x dx dt. Okay, and then in step 5, after completing step 4, okay, then you would substitute all known values for the rates of change and the variables, and then you would solve. Now, one of the mistakes that's often made is that when you're given values for specific variables, people plug them in first before they take the derivative. So here, do not substitute numerical values in before performing the differentiation unless the number will remain constant, okay, over time, meaning it's not going to change. Okay, for example, if you have the length of a ladder, this ladder will not change. It's not an expandable ladder. It will be a constant value, meaning then that derivative would become 0. If you do this, meaning you make this mistake, you're going to end up with a derivative of 0, and that's a huge error. It sort of defeats the purpose of the whole problem. So I'll go through 2 examples on this page and then one more example on page 11. So this first example is very basic. You're given this function here, and it says given that dx dt, meaning the rate of change of x with respect to time, is equal to 1, we need to find dy dt when x is equal to 2. And what that means is it's telling us that we're going to take the derivative of this function right here with respect to t. So before we were just taking the derivative with respect to x. When we took the derivative of x, it was 1 dx dx. But because we are deriving with respect to time as indicated here in this problem, we need to take the derivative of x with respect to time, which would just be dx dt, because the derivative of x is 1, okay, plus 4 dy dt, and this is equal to, in this case, this is a constant, so it's just 0. We are told that dx dt right here is equal to 1, so I'll make my substitution. So what we have is 1 plus 4 dy dt is equal to 0, and we could proceed to solve for dy dt. Subtract 1, treat this like a variable. 4 dy dt is equal to negative 1, divide by 4. So it said find dy dt when x is 2. Well, in this case, because the x derived out, meaning the variable x is no longer here, you don't even have to make a substitution. So dy dt is equal to negative 1/4. That would change if this function changed, but that's what our function is. Here, in example 2, this is actually how you would be given one of these word problems, and it says that a stone is dropped into a still pond that sends out a circular ripple whose radius increases at a constant rate of 2 feet per second. So the radius increases at a constant rate. So this is the rate of change of the radius. Okay, and it says how rapidly is the area enclosed by the ripple increasing at the end of 12 seconds. So how rapidly means how fast or at what rate. So we are looking for a rate at how the area is changing. So first of all, when we have the area of a circle, we'll be using area is equal to pi r squared. Okay, so here we have two variables. Pi is not a variable. So we need to determine what is going on with my area and what is going on with my radius. So what they are telling us here is that the radius is changing or increasing at a constant rate. So that means here when they give me a rate, this is the derivative of the radius with respect to time. So they give me dr dt, so these are words that you need to look for, is 2 feet per second. Okay, so that's an important piece. How rapidly or at what rate of change is the area changing? So they want to know dA dt, that's my unknown value, at the end of 12 seconds. So they give me a time, but you notice here we don't have a variable t. Okay, so we have a bunch of stuff here. What we need to figure out is what do we need and what do we not need. So what we need to do is take the derivative of my formula here. The derivative of a with respect to time is dA dt is equal to, remember pi is a coefficient. Okay, so when you take the derivative of r with respect to time, it will be 2, and I'm going to put this pi here, r dr dt. Okay, dA dt is what they want to know. This is my unknown value. Okay, we have dr dt. They gave us that. It's right here. So in terms of variables, I'm missing my radius. So we actually have to go back and think about some of these relationships here. And what they're saying is my radius is changing at a rate of 2 feet per second. So let's see, for r, we're changing at a rate of 2 feet per second. So for those of you that remember this, they want to know how rapidly the area enclosed by the ripple is increasing after 12 seconds. So my seconds will cancel out. So I actually have my radius. It's 24 feet. So I needed this. So that way I can make that substitution. So now they want to know at what rate is my area going to change given 2 pi times 24 feet times 2 feet per second. Okay, so now we're just going to multiply. So let's see, this is 48 times 2 is 96 square feet per second. You must include your units. If you do not include your units, you're just saying 96. 96 what? Bunny rabbits. Make sure you include your units.